Hello everyone, I'm Frank Devlin with APA, the Engineered Wood Association. Welcome to the first in our series of Engineered Wood Products training webinars. Today's topic is an introduction to engineered wood products. Our presenter today is Darren Graham, an engineered wood specialist with APA based in Houston. Aaron studied construction management at Brigham Young University and has 16 years of experience in the engineered wood industry. Darren has been recognized for his national sales efforts and also for his work as an engineered wood products trainer. Once again, welcome to today's webinar. Darren, I'll turn it over to you.
Well, thank you, Frank, and welcome all. It's great to start our Engineered Wood Products training series. Now, this is the first in APA's training series on engineered wood products. I'll be presenting APA recommendations and specifications on engineered wood products. Individual manufacturer recommendations may differ, so you should always consult appropriate manufacturer's literature when specifying any engineered wood products. All right, well, for today, we've got some training objectives, and upon completing this training, you should be able to identify and describe the various types of engineered wood products, their significant features and benefits, their significant characteristics, and of course the appropriate applications or uses for each. So let's start by, of course, talking about what are engineered wood products. Engineered wood can be described as any wood-based building material that has been improved physically by a man-made process. Today we'll be talking about a group of structural wood products manufactured using veneers, wood strands, and solid wood. I-joists are typically used as floor joists and roof joists. Glue-laminated timber or glulam are typically used as beams and columns. A group of other products are classified as structural composite lumber or SCL. SCL products are laminated veneer lumber, LVL, oriented strand lumber, OSL, laminated strand lumber, LSL, and parallel strand lumber, PSL. SCL are used for a variety of structural applications including beams, headers, and occasionally columns. Now, all of these names and acronyms may seem a bit confusing, but we'll clear the fog today in this first training segment. These products are primarily used in wood frame residential and light commercial construction. Now, there are many beneficial features of engineered wood products, and one of the most important is that these wood-based building products are engineered for structural applications. They're designed and manufactured to maximize the natural strength and stiffness characteristics of wood by optimally orienting the wood strands, veneers, and laminations, and by combining wood with durable adhesives. The products from these manufacturing processes also have consistent dimensions. Engineered wood products are both straight and stable, with very predictable length, strength, and stiffness properties. The column and beam members are produced in long sections of 48 feet or longer that can be custom cut to meet a nearly unlimited variety of applications. All of these products are manufactured to standards that are internationally recognized and provide consistent design values that are supported by continuous quality control with third-party oversight. Therefore, builders and designers can use these products within their projects with confidence in their structural performance and durability. Another key reason for their popularity is the longer lengths that are available, resulting in fewer pieces to purchase and increased design flexibility. Using fewer pieces increases profitability since less framing is needed and time is saved during cutting and fitting. Longer spans provide the designer with more options for use of the interior space by increasing spaces between supporting walls and beams, resulting in more saleable floor plans. Stronger members can also mean fewer pieces because floor joist spacing can often be increased. Now, long lengths and pre-cut framing packages also result in less waste, which impacts the amount of material going to landfills, and that, of course, results in reduced disposal costs. Using conventional framing lumber, as much as 10% of primary framing members are rejected due to cutting or excessive cupping, splitting, warping, etc. This rejected material gets thrown away or cut up for use as blocking or other applications that would not normally call for the use of the more expensive lumber grades. That's not an issue with EWP. So not only are these products manufactured from a sustainable and renewable resource, their use in the structure is environmentally positive as well. Now let's take a few minutes to consider the manufacturing of engineered wood products and how it maximizes the structural value of our timber resource. As we noted earlier, engineered wood is any wood-based building material that has been improved physically by a man-made process. We'll look at some of those processes. The timber resource is sized to make laminations or layers of the engineered wood products at state-of-the-art plants. They're high-speed operations that convert the logs into precise components based on the species and grade of the wood. The efficiency in evaluating, selecting, shaping, and bonding these components is what makes engineered wood cost competitive with other building products. The raw wood laminations and strands are sorted by grade and dried so that the resins can effectively bond the laminations or strands together into structural members. The resins are applied to the laminations and strands in a controlled manner to assure a permanent bond. Strong wood fiber plus durable moisture-resistant resins equals high-quality engineered wood products. In order to design a durable, high-performance product using our wood resource, you have to take into consideration the natural properties of wood, the orientation of the grain in the wood laminations and strands that impacts structural performance. Another consideration is that the wood moves as it increases and decreases in moisture content. With engineered wood, the wood members will typically increase in size slightly following manufacture. Wood is stronger, of course, when dried, and until we can grow trees without limbs and branches, there will be characteristics in the wood such as knots and sloping grain that reduce its strength. All of these properties are addressed in the design of engineered wood products and systems. Wood is primarily made from parallel tubular structures. On a microscopic level, we can model wood behavior using a bundle of straws. When compression is applied parallel to the grain, the straw bundle is strong and efficiently resists crushing. If load is applied perpendicular to the length of the straws, or perpendicular to the grain, the straws crush more easily. This is similar to wood, since a lower force is required to cause crushing or failure perpendicular to the grain. This illustrates the anisotropic nature of wood, different strength properties in 3 different directions: longitudinal, which is a strong direction, tangential, which is weak, and then, of course, radial, which is the weaker or weakest. Now, continuing with the analogy of wood cells being like a bundle of soda straws, in compression, wood is utilized vertically as studs, columns, and posts. It is also used in compression in truss assemblies such as at the top chord and some web members. Compression applied perpendicular to the grain is weaker than if applied parallel, since it crushes more readily. In tension, wood performs well with the load applied parallel to the grain, as long as the grain is straight and there are minimum knots and other strength-reducing characteristics. This is the most demanding application for wood performance, and these applications in general require higher quality than compression members. Bending of beams is usually a combination of compression on the top of the beam and tension on the bottom. We'll look at this more closely in the next training module. When wood decreases in moisture content, the walls in the tubular-shaped wood cells shrink, causing the wood to decrease in dimension in both thickness and width. In wood science vernacular, the shrinkage that occurs perpendicular to the growth rings is called radial shrinkage. Shrinkage that is parallel or tangent to the growth rings of the wood is tangential shrinkage. Tangential shrinkage averages about twice that of radial shrinkage in most species. Shrinkage in the length of the wood or longitudinal shrinkage is negligible. In most construction lumber, the growth rings are parallel to the wide face. That is why solid lumber floor joists shrink in depth as they dry to a stable moisture content, which is normally found inside a completed structure. Because engineered wood floor and roof systems use low moisture content I-joists, LVLs, and rim board material, it's recommended not to mix lumber into that system because of both the potential shrinkage of the lumber and the potential minor expansion of the I-joist. As you can see by this example, loads will not be distributed evenly if joists are not the same size. The first engineered wood product that we'll discuss is the wood I-joist. I-joists optimize the wood resource in the shape of the letter I. When I-joists are used to span between supports as floor joists or roof joists, bending forces are carried in the top and the bottom flanges. I-joists can also be used for rim board, headers, and studs. The flanges are manufactured from either laminated veneer lumber, LVL, or machine stress rated, MSR lumber. We'll talk more about LVL in a few minutes. In order to precisely determine the performance of the lumber flanges, the lumber is not only visually graded, as it is most construction lumber, but stress rated by specialized equipment to determine the lumber's ability to resist bending forces. The web material is typically a 3/8-inch oriented strand board, OSB material, that has been manufactured using specifically sized and shaped strands of wood that have been bonded together under heat and pressure into sheets. The flanges and web material have all been specifically manufactured for use as components in those I-joists. The efficient use of the wood fiber creates a joist that not only contains 36% less wood than dimension lumber in 2x10s and 2x12s, but is stiffer and stronger as well. I-joists and other engineered wood products make optimum use of the renewable resource by putting high-strength wood only where it is most needed. According to the most recent builder survey, home builders choose I-joist framing for use on about 50% of the raised single-family floors in the United States. There are many reasons for the consistent popularity of I-joist floor assemblies. Solid lumber is used in about 1/3 of residential floors, and wood trusses are about 17%. The other category includes things like steel framing and structural insulated panels. So why engineered wood products? These lighter weight joists also come in long lengths so that handling is easier with the possibility of running a single joist from the front wall of a building to the rear wall. Engineered wood floors go up quicker than other floors when installed by experienced framers. Engineered floor systems offer value in many ways to the builder. I-joists create a flat system with all of the components exactly the same depth. With few variations in the joists and rim board products, the connection between the joists and subfloor panels is more direct by providing a smooth, uniform surface for the continuous bead of adhesive and nails so that all of the floor components are securely connected, and then they move together as a single unit. And as we all know, it's the independent movement of the components in floor systems that create noises and uneven floor surfaces. Positive connection of these components results in reduced callbacks and increased profitability for the builder. I-joists are consistent in size, straightness, and strength, and provide consistent performance within a floor, which means flatter and quieter floor assemblies. And with today's rapidly increasing energy code requirements, it is more important than ever for ductwork to be in the conditioned space of the building, rather than in the attic or crawl space. With properly designed ductwork running through the floor system, there's less wasted energy and greater confidence in meeting the requirements of the energy code. As shown in this picture, the ability to cut appropriately sized and positioned holes in I-joists facilitates the running of ductwork perpendicular to the joist, and the possibility of increasing the spacing between the joists allows larger ductwork to run between them. These opportunities are maximized with the cooperation of the floor designer and, of course, the HVAC contractor. I-joists are manufactured in 5 standard depths, including 9.5, 11 7/8, 14, 16, and 18 inch. Some manufacturers may also produce other depths. The joists are proprietary to the different brands and utilize different flange materials of various widths and thicknesses. The structural performance of I-joists varies from one manufacturer to another, so in order to design with I-joists, you must use the structural characteristics and installation recommendations provided by each provider. Laminated veneer lumber, or LVL, is the most widely used type of structural composite lumber. It uses specially selected, ultrasonically graded, kiln-dried veneers and orients all of the veneers with the grain running lengthwise. Veneers are lap joined to create long lengths. We learned earlier in this presentation, wood fiber is strongest in tension parallel to grain, so orienting the grain in all of the veneers of LVL to the length of the member maximizes its ability to support bending loads. LVL is used for beams, headers, rafters, scaffold plank, rim board, I-joist flanges, and studs. LVL beams are commonly made in depths matching the depths of I-joists. Larger depth LVL is readily available as well. The most common thickness is 1 3/4 inch, but LVL is available in thicknesses up to 7 inch. They are commonly available in bending stiffness or modulus of elasticities ranging from 1.5E to 2.0E. Parallel strand lumber, or PSL, is manufactured from veneers that are clipped into long strands and bonded together in a parallel formation. Once again, the grain is running in the direction of the length of the beam member to maximize the bending strength. The strands are cut into lengths that are around 300 times their thickness. This product is commonly used in headers, beams, studs, and rim board. At this time, this product is proprietary to one manufacturer. PSL is manufactured in the same depths as I-joists and LVL and in thicknesses of 1 3/4 inch, 3.5, 5.25, and 7 inch. The members are also manufactured with similar structural characteristics as LVL of 2,900 psi in bending and 2.0E in bending stiffness or modulus of elasticity. And here are other additions to the structural composite lumber family. Laminated strand lumber uses strands with a ratio of around 150 times their thickness. These products are commonly used for wall studs and headers. Oriented strand lumber uses shorter strands that are around 75 times their thickness. The common application of OSL is for wall studs. LSL and OSL are manufactured in 7.25 inch depths as well as the I-joist compatible depths. The common thicknesses are 1 3/4 inch and 3.5. Their common stiffness values, or MOEs, are 1.35E and 1.55E. Check with the manufacturers for additional information on structural characteristics and, of course, availability in your area. Now, the last product that we'll talk about is glue laminated timbers, or Glulam. Glulam uses layers of 1.5 inch or 1.5 inches and 1 3/8 inch lumber that are bonded together in a flat stack. The wood grain runs parallel to the length of the beam, as we've seen with all of the engineered beam products. It's commonly used for headers, beams, studs, and columns. Glulam are available in a variety of depths, including I-joist compatible depths. Common widths include 3 1/8 and 5 1/8, as well as 3.5 and 5.5 inch to match the common framing width. As with the other engineered wood products, they are readily available in lengths up to 48 feet. Their most common structural designation is a strength of 2,400 pounds per square inch, or PSI in bending, and then a stiffness or modulus of elasticity of 1.8E. Also, 3,000 PSI 2.1E Glulam is available. There are also many other sizes and custom shapes that are available on special order. There will be a separate training module for Glulam products coming up later in this webinar series. Engineered wood products that bear the APA trademark are manufactured in accordance with APA or national standards. The trademark is the manufacturer's assurance that the product conforms to the standard noted on that trademark. APA members are committed to APA's rigorous program of quality inspection and testing. Many engineered wood products are proprietary and use proprietary engineering standard reports and APA product reports as well for their code recognition and product use and design information. Here's a picture of an APA product report. These reports indicate that the product meets the intention of the building code when used as identified in the report. Product reports identify the specific design uses and limitations as well as the design properties. These reports are available for free download on the APA website at www.apawood.org. Wood I-joists are typically designed as either floor joists or roof joists that directly support the floor or roof sheathing materials and coverings. They are sized to carry both the dead loads of the floor or roof system components and the anticipated live loads that will be applied in the use of the space. This slide and the next several slides show some typical uses of engineered wood systems. Here, I-joists are being used as repetitive floor joist members. Note that in the foreground, the I-joists are hanging from an engineered Glulam beam supported by a Glulam column. The I-joists in the background are used as floor joists in a continuous span over an intermediate bearing wall. In this photo, we once again see I-joists used as repetitive members being supported by lightweight metal hangers on the side of the engineered wood beam at the ridge and the exterior walls. In this application, the I-joists are being used in a simple span or single span condition. In this case, the I-joists are being used as cathedral ceiling joists on a gable-type roof and will be supporting both the roof and ceiling loads. Here we see a grid of LVL floor beams being positioned in a large house. Note that in some cases, the LVL beams are being used to support other LVL beams that are being installed perpendicular to the lower beams. Often LVL beam members are used in a hidden or flush beam application. Here the I-joists are supporting the floor above and in turn being supported by lightweight metal joist hangers on each side of an LVL beam. The beam is the same depth as the floor joists, so that when the ceiling is applied to the bottom of the I-joist, the beam will be fully concealed. In this shot, an LVL is being used as a header to carry the load over an opening in the wall. LVL headers are also commonly found in longer spans, such as seen here in a double-car garage opening. It's likely that a header of this length is either a thick 3.5-inch LVL or has two laminations of LVL fastened together. Because engineered wood is straight and relatively lightweight, it makes installation efficient. Now in this photo, LVL is being used as a column in an I-joist studded wall system. I-joists are not typically used as framing members in walls, but are used this way in some very high efficiency passive energy home designs. Here's another wall using several different engineered wood products. In this application, OSL is used as the top wall plate and the framing around the rough opening. Also note the I-joist and LVL studs in this thick wall assembly. We often see OSL, LSL, and LVL studs used in walls 12 feet or higher and greater because of their straightness and their bending strength. In this photo, a double lamination of laminated strand lumber, or LSL, is being used as a short support beam for a wall above. Here's a photo of parallel strand lumber used in a tall wall application for both vertical and horizontal members. This picture is a parallel strand lumber beam. It's being used to carry the end of a span of roof trusses. Now in this picture, we have glulam being used to support I-Joist floors. All of the beams are top-loaded, and a very large hanger is supporting the glulam that is hanging on the other glulam. Here, a 2.5-story window wall is being supported by glulam, vertical columns, and horizontal beams. Now, it's important for all of us involved in the wood products industry to understand how remarkably earth-friendly the products that we sell really are. Wood, and more specifically engineered wood, is a renewable building material and is a good choice for the environment, for green building, and for long-term life cycle performance. With intensified interest in environmental impact and green building, it's important to consider these attributes. And these are some U.S. forest facts. Approximately 1/3 of the U.S. is forested. That makes out to be 766 million acres. But only about 500 million acres are open to logging. The volume of annual net forest growth is currently 2 times higher than the volume of annual harvest. And in the U.S., forest planting averages about 2 million acres per year. So engineered wood really is a green choice. Manufacturing of engineered wood products is resource efficient and energy efficient. Manufacturing techniques have evolved to maximize use of fiber and energy. The industrial output per unit of wood input increased 40% over the last 50 years. Over half the energy consumed in manufacturing wood products is actually bioenergy. And the U.S. wood products industry accounts for 60% of bioenergy production and use. So why engineered wood products? Well, again, predictable performance, uniform weight and strength, the systems are quick and easy to install, the components are dimensionally stable, they're lighter in weight and easier to handle, and of course, they make efficient use of the wood fiber in the manufacturing process. Now here is a picture of a green verification report. Many of APA's member manufacturers have developed green verification reports. These reports help building officials and design professionals to determine a product's eligibility for points under the recognized green building standards. APA issues these reports to document the compliance of an engineered wood product that is manufactured under a quality program. Now this concludes our introduction to engineered wood products. Before we sign off, I'll review the training objectives and then review some APA resources you may find useful. So again, our training objectives for today were to make it so that you would be able to identify and describe various types of engineered wood products, their significant features and benefits, their significant characteristics, and the appropriate applications or uses for each. Now, both the 2012 and 2015 versions of the International Residential Code, or the IRC, include fire protective membrane requirements to enhance the fire performance of residential floor systems. The APA has a wealth of information about designing I-Joist floor systems to meet the IRC requirements, including a recorded webinar you can watch online, as well as downloadable publications and CAD details. If you have questions about I-Joist and fire protection, visit www.apa.org/I-Joist fire assemblies, where these resources, of course, are available for free. Now, the APA has many other resources available for you as well. We all need help from time to time, and the APA's Product Support Help Desk is a great source for answers to those questions that you run into during your work with engineered wood products. The Help Desk is a free service and is available to answer your questions pertaining to the specification and application of engineered wood products and systems. It's staffed by specialists who have the knowledge to address a diverse range of inquiries related to engineered wood. It's not only a fantastic resource for you, but also for your customers, builders, designers, and code officials. The APA Field Services team consists of full-time engineered wood specialists located throughout North America. These engineered wood product professionals include engineers, architects, and construction experts who are available to provide information and recommendations to construction and design professionals. We recommend you get to know the APA engineered wood specialist in your own area. The APA has updated and redesigned the www.apa.org website. The site holds a wealth of information about products and their recommended installation requirements, and all electronic downloads are free. Take a few minutes to explore the site so that you're familiar with the resources that are available. Also on the APA website is a list of all APA members, including complete lists of the manufacturing facilities and their sales contacts. APA has a large selection of literature, some of which will be referred and referenced to during these training modules. All of these documents are available for free download from the APA website. From the apacad.org website, designers can download many different details that can be dropped directly into their designs. Now this concludes our training module. Do you have any additional questions?
Good content. We did have some questions come in while you were speaking, and let's get to those right away. What is the APA doing to educate builders with regard to I-Joist fire protection issues?
Well, this question, of course, relates to the IRC, or International Residential Code requirement, that's been adopted recently in some states. It requires fire protection in most lightweight floors, including web wood trusses, I-Joists, and of course steel framing. We've recently added several new assemblies to our systems report, which is SR 405, and we'll have a webinar coming up that will be dedicated to that topic. Stay tuned, and we'll post details on our website for that.
Very good. Now, you didn't cover cross-laminated timber today, or CLT. Does APA consider CLT an engineered wood product?
Yes, we do. We didn't cover it because it's primarily a product that's not distributed by wood product distributors. Since it's new to the market in North America and it's not sold through the typical channels, right now it's being sold on a project-by-project basis. So since we're dedicating this series primarily to wood products distributors and dealers, we didn't include the CLT in this presentation. I should say again, there's 4 manufacturers of CLT in North America, and they all produce product to the APA standards, but again, we didn't cover it today because it's not typically distributed through the setup channels that we're talking about training to at this time.
Very good. Now, whose products are APA rated?
That one's an easy one. If you go to our website, apawood.org, and look under the manufacturer directory, there's a full listing of the members and the manufacturers and the products they produce. You can also do a search there and search by product, manufacturer, or even the mill number for the product that you're looking at.
Very good. And finally, how do I find out who my local APA tech rep is?
Again, another easy one. Our website, apawood.org, and look under About Us, and there's a staff contact section with a listing of all the local engineered wood specialists.
Very good. Thanks again, Darren. And that concludes today's webinar. We thank everybody who attended, and we hope to see you at our next webinar.